Hello, and welcome to our course on differentiable graphics with TensorFlow. My name is Cengiz, and obviously this is not a live course. We're just recording this, but we'll try to make it as lively as possible. So in this course, we will walk you through differentiable and neural scene representations and renderings. So hopefully it will be a quite interesting course for you. So we will introduce you to our TensorFlow API called TensorFlow Graphics. This is an API for easy and convenient implementation of differentiable graphics layers, which you can use in a lot of problems that actually we will be talking about in this course. And by the end of the course, we hope that you will have a solid understanding of state-of-the-art techniques and already start your own experiments and with differentiable graphics to solve interesting inverse problems. But before we go into any of these details, first and foremost, I would like to start with a big thank you to all our past and current contributors. I really appreciate our community, and none of these would have been possible, of course, without their continuous support and enthusiasm. So a big thank you to the TensorFlow Graphics community. And as for this course, this is a team, and this is actually me. I'll basically start by giving an overview of why we care about this and how we do everything in TensorFlow graphics, a bit like a high-level overview. And then we will actually go into a bit of details on differentiable rendering and differentiable scene representations, how we actually use this in practice to solve interesting problems and challenging problems, and how we define certain things in the library. So we will actually go through pretty much all the details you need to get started with actually latest and greatest techniques in this area to solve some of the most challenging problems in the field. So, but before, let's step back for a moment and define what we mean actually by computer graphics, because we will be talking about differentiable computer graphics, right? So computer graphics is a subfield of computer science, officially, that studies methods for digitally synthesizing and manipulating visual content. So this is what computer graphics is. And obviously, over the last decades, thanks to, of course, all the research, the excellent researchers in the field have been conducting, we have seen amazing advances in achieving these goals of computer graphics, synthesizing and manipulating visual content. So we can now render beautiful synthetic scenes photorealistically with all the intricate details. And we know how to model such detailed scenes with advanced models for geometry, appearance, motion, lighting, cameras, and more. So we have this really nice scene representations with all the details of the scenes, and we know how to use them to render and to generate nice synthesized images. And nowadays, basically, we have the scene description in pretty much all computer graphics systems. This definition consists of the scene entities, such as geometry, lighting, motion, transformation, camera models, materials and appearance, and some scene semantics. And then computer graphics provide us with the tools to represent all these components and render them to generate images. So this is what computer graphics is all about. And these definitions and resulting renderings are, I think, some of the greatest achievements actually of computer science over the last decades. So there is great potential to utilize these representations and the techniques we've been developing actually to solve further problems. And the idea here, the idea of differentiable graphics, is that once we can define this whole process, the forward process, basically going from scene definitions to images to projections, we can actually, if we can make everything machine learnable, we can actually also define the inverse process. So we can go from the images back to the parameters of the scene entities we have. And as we will see, this has a lot of exciting applications and different areas where this is actually quite important. And just to give an idea, for example, we can go a bit further and we can say, well, we define neural networks that actually reparameterize the parameters we have for the scene entities. And then what we can have is an end-to-end system where we can start with an image, if we have an image, for example, a photo taken from the real world, and basically we use our rendering part, the indifferentiable graphics part, to again render an image and just define a loss between these two images. And as you can imagine, this is actually super important since we have access to a much less amount of labeled data. So unsupervised data is much more abundant. It's really important to have such setups where we can also work with unsupervised training settings and with unlabeled data. And this already brings us actually to this almost dual field of computer vision. So I wanted to also briefly mention what we mean by computer vision, because we will be seeing a lot of computer vision applications throughout the course. And basically, computer vision, the definition is that it's concerned with the theory behind artificial systems that extract information from images. So this really fits actually into this framework we have. And if you think about it, this differentiable graphics idea is bringing these fields together. So it's really bridging the gap between these two fields, and we can, as I said, we can define everything as a forward and inverse process. And as you will see in this course, we can actually solve a lot of interesting problems by utilizing these ideas. So just some example problems to start with are the following. For example, if you would like to estimate the 3D position and orientation of an object, so like, for example, a sixth of tracking setting, you can use such ideas. If you want to understand the material properties of that object, you could also use a similar differentiable computer graphics and rendering system. If you want to detect and recognize objects in an image, if you want to track poses, etc. So for all these cases, for all these problems, which are normally ill-posed and actually they're the topic of computer vision most of the time, we can actually use the idea of differentiable graphics. So it's a pretty important, I believe, setting and framework to utilize what we've been developing over the last decades. And obviously, answering such questions about the three-dimensional world is fundamental for many applications in practice. I think a good example is autonomous vehicles and robots, which are very important and really in a fast pace being developed these days. So in these cases, these machines actually, they need to reason about the three-dimensional objects and their relationships in space continuously. So it's really important to train machine learning systems to tackle such complex 3D tasks. As you might imagine, typically for these cases, a large quantity of data is needed. And labeling such data in practice is a very costly and complex process. So as I mentioned a couple of slides before, it's thus very important to have mechanisms to design machine learning models that can reason about the three-dimensional world without much supervision. So our techniques really come into picture for such cases, and they're really handy. And in general, combining computer vision and graphics techniques really provides this unique opportunity to leverage the vast amount of readily available unlabeled data, which we can basically use to sense the real world, so we can realize a new form of 3D digital reality. So as we will see, there's so many different cases that are extremely useful in practice. And we will be talking about this as we go along, and you will also see how practically this can be implemented in this framework. So overall, this course is devoted to providing, again, a thorough understanding of all these, of the state-of-the-art of differentiable graphics, and in practice, how we can actually utilize this knowledge to develop robust and usable systems to solve such challenging problems and beyond. We will be illustrating a lot of examples, a lot of also code, and basically this is also an opportunity, I think, to get started with these techniques easily with the framework. So I hope you will enjoy the course, and you will get basically a thorough understanding and some practical knowledge of all these in this course. So we have a couple of guiding principles for TensorFlow graphics, which I believe very important. And as you will see, as you use the system, the library also quite important. So first of all, we really want to deliver a library that basically has the best experience possible for the developers, so that we can get easily started and you can really have an enjoyable experience with the library. And then we really want to have a well-tested and robust library, so we can really rely on the features we have without too many bugs, and hopefully quite robust techniques all throughout the library. And lastly, we would like to continuously, and we have been continuously implementing and integrating latest and greatest techniques into the library to just basically keep up with the pace of this really fast moving field. So you will find implementations of a lot of techniques, which I think is also very handy if you want to work with some of those for your day-to-day problems. So let's get started with the course, and hopefully you will enjoy this course. Just as an overview, and then I'm done with the introduction. This is the plan that will be held. So we will actually start with a bunch of demos, as you will see. And those are, I think, great demos to just illustrate how you can use a library in practice. And then we will dive into a bit of details for differentiable rendering with rasterization, and differentiable volume rendering and mirror radiance field. So you will actually learn a lot about how you develop differentiable rendering systems, which is, of course, a fundamental component of everything we do in differentiable graphics. And then we'll talk about how we represent certain scene elements in the library, such as geometry and transformations, etc. And then also we'll talk about the frameworks we have as part of the library. And finally, we will talk about the data sets and data pipelines that are already integrated into the library, which are, I think, also great to accelerate research and development. And yeah, so hopefully this will be an enjoyable course for you, an informative course for you. So yeah, let's get started.